this video, we will cover part 3 of chapter 14. Water is used for many different industrial activities and manufacturing. In table 14.4, we can look at some industrial products and the amount of water that's required to produce these materials. These are some of the hidden costs of water. For example, in order to build a laptop computer, 10,600 liters of water is required. Water isn't just used in the home in sinks, faucets, showers, and dishwashers, but there's a hidden cost of water for a lot of the different products that we acquire. Outside of industrial use, a large amount of groundwater is used for drinking water. Over half of the population in the United States gets its drinking water from sources of groundwater. One of the difficulties with this is that the groundwater is difficult to clean and can be easily contaminated from a variety of different sources. The water that we get in our sinks and faucets is treated in a variety of different ways to ensure that it's clean and safe to drink. One of the major contaminants in groundwater are the nitrate compounds. Contamination of nitrates occurs in areas with a lot of agricultural production. Fertilizers are used in order to boost the yield of crops. When runoff occurs, it can be contaminated with fertilizer and animal waste and enter the water stream this way. The nitrates are extremely soluble, so they will readily enter the water streams. Nitrates can be metabolized into nitrite ions, and the nitrite ions are the source of the condition known as blue baby syndrome and lead to negative health effects and even death. This figure is a heat map that contains the probability of nitrates exceeding 4 milligrams per liter in concentration. One thing to note is that areas with a high amount of farming correlate to a high amount of nitrate concentration. We can see in the Midwest as well as Central California, areas that have extremely lucrative agricultural industry, that there's also a much higher concentration of nitrates in the shallow groundwater. We have looked at contamination based on volatile organic compounds in the air pollution chapter, but these are also present in water. The VOCs can contaminate the groundwater and add potentially toxic and carcinogenic molecules to the water, as well as undesirable odors. Many of these volatile organic compounds originate through industrial activity, wells, landfills, or leaky storage tanks. Whatever the source of the VOCs is, they all have the negative effect of contaminating our groundwater. So how much water does a single person use per year? Well, the number might astonish you because a lot of the water is used in hidden costs. We have more than 170,000 public water systems in the United States, and the amount of water per person that is used is almost 2 million liters. The major source of this 2 million liters per year is industrial and agricultural purposes. Personal purposes is a much smaller amount. Per capita, the United States has the highest use of water. In order to ensure the safety of our water, the Safe Drinking Water Act was passed in 1974. It has been amended since then to account for some recent breakthroughs in science and chemistry. The Safe Drinking Water Act regulates the standards for contaminants that are found in our water supplies. This legislation posts standards for every substance that can be considered a contaminant. In the left-hand column, we have the substances. Examples of these are inorganic compounds and organic compounds that are known carcinogens or toxic to human health. In the right column is the concentration of this contaminant that's allowed by law. If the concentration of any of these contaminants exceeds the level of the U.S. Environmental Protection Agency Drinking Water Act, then that water cannot be sourced for personal use. When we are analyzing water samples for different pollutants, parts per million and parts per billion are also used to describe these quantities. The circumstances which we would want to use parts per million or parts per billion are when we're looking at a very small amount of a substance dissolved in another substance. Parts per million, for example, is equal to 1 gram of solute for 1 million grams of solution, and parts per billion is equal to 1 gram of solute per 1 billion grams of solution. If a substance, for example, were to have 100 parts per million, that means they would have 100 grams of solute for every million grams of solution.